Hello everyone, welcome back to our channel. Today we will understand two special and important boundary conditions called Robin boundary condition and periodic boundary conditions. These two conditions are very critical boundary conditions and sometimes they can significantly impact the convergence of your overall network. Unlike Dirichlet and Neumann boundary condition, Robin and periodic boundary conditions add a level of complexity that can make it much harder for the model to converge. So for instance, with Robin boundary conditions, so we are setting up a requirement that balances the function value with its derivative at this particular boundary. So this can create a tough scenario for the network where it has to manage not only the function value but also its gradient very precisely. Similarly, the periodic boundary conditions on the other hand demand the solution to be continuous across the boundaries. This means the model must ensure the function values match at two edges, that is at -1 and 1 in this particular example. Often sometimes it also involves matching the derivatives to ensure smooth transition across boundaries. Meeting these special boundary conditions like Robin or periodic boundary conditions while still satisfying the original governing differential equations and other boundary condition is a very critical task. Sometimes these may even introduce instability in training, which can lead up to poor network solutions. So with these challenges in mind, in today's tutorial, we are going to focus on proper implementation of Robin and periodic boundary conditions in DeepXDE. We will go through each boundary condition, Robin and periodic boundary conditions step by step, discussing the functions and configurations required to set them up correctly in the code. By the end of this tutorial, you will have a clear understanding about how to apply these conditions effectively in DeepXDE. To explain these concepts, I have set up two examples of differential equation. So this first set is to explain the Robin boundary condition and this second set is to explain the periodic boundary conditions. Both these examples use the same Poisson equation that we solved earlier in our previous tutorial, that is this tutorial. So the differential equation and the basic setup and the other neural network parameters like the layer size, activation, initializers and other neural network parameters are same as this tutorial. So I have not made any modifications in this. So in this tutorial we will explicitly focus on the Robin BC and the periodic BC. Let's first look at the Robin boundary condition. Robin boundary conditions are a mix of Dirichlet and Neumann boundary condition. So for example, in the Dirichlet boundary condition, we apply the boundary condition explicitly on the function value. And in the Neumann boundary condition, we put the boundary condition on the derivative of the function value, that is du by dx, whereas in Robin boundary condition we mix up these two conditions. So we will create a certain condition where it has to satisfy both the function value and the derivative value, and this condition is written in certain format like this: au plus b du by dx is equals to z, where a, b and g can be constants or can be some functions. So in DeepXDE, so within the ICBC module, we have a separate class called Robin BC. Using this Robin BC class, we apply this condition just like Neumann BC and other Dirichlet BCs. So this also takes three conditions: the geom, boundary value and the boundary condition. So here the boundary value and boundary conditions are two separate functions itself, okay, two sub functions. Here, the boundary condition function verifies whether the given points on the geometry are there on the boundary condition where we specify this Robin or not. So this boundary condition is defined here. So it verifies whether the given set of x coordinates are on the boundary or not. This boundary condition function, that is this boundary condition function, here it is boundary r. So this takes only two arguments. So the first argument is the coordinates. So here x represents the coordinates. In a only case, x represents only the x coordinates, but it is general actually. In a partial differential equation format, you can have multiple variables here. Okay. So on boundary is a Boolean value that I said before. So here the boundary R takes only two arguments, that is the coordinates and this on boundary condition. So we will check whether the given set of coordinates are on the boundary or not. If it is there on the boundary, we will return a true. If the value is not there on the boundary, we will return false. And this boundary value it itself is also a function, and this boundary value takes two arguments. First is the x and second is the y. So these are the function input and outputs. Okay, it only takes these two arguments. That's it. These are all some of the examples where we see this kind of Robin boundary conditions. So in heat transfer with convection, we apply Robin boundary condition like this, and in some chemical diffusion we see a Robin boundary condition like this, and in electromagnetic field with impedance boundary we see a Robin boundary condition like this actually. So when we set up the Robin BC like this, so here at right we have applied this boundary condition BCR, and within the data I just passed this BCR into this data object. So here BCL represents the Dirichlet boundary condition and BCR represents the Robin boundary condition, and similar here 16 represents the total number of collocation points that we are taking inside the domain, and this 2 represents two boundary points, one on the left and one another one is on the right, and this one is the solution. So we do not use this solution anywhere in the training, but this solution is used to evaluate this relative error, and these are the total number of tests. We define the neural network like this, so with 50 hidden neurons and 3 layers, and a tan H activation function for all the hidden layers and neurons, and glow rot uniform. Using this initializer, we initialize the initial sets of weights and biases. Using these conditions, we set up the neural network. So using this neural network and this data module, we show the compile here actually. So and here, so this basic model.train does the train. So here we are using 10,000 iterations. This is the overall loss pattern that we are getting. So as I said before, this is the governing differential equation loss, and this is the Dirichlet boundary condition loss, and this is the Robin boundary condition loss from train, and similarly this is the loss values from the testing, and this is the overall test metric. So these are all the overall loss values that we have got at the end of the train, and when we plot the final values like this, we get a solution like this. So if you notice here, the analytical solution u of x is equals to x plus 1 whole square. It is the same solution that we have seen with Neumann boundary condition as well. So this occurs because the solution u of x is equals to x plus 1 whole square satisfies both Neumann and Robin boundary conditions at x equals to 1. For example, at x is equals to 1, the Neumann boundary condition is du by dx is equals to 4 that we have applied here. This, and here at du by dx is equals to u that we have applied here in Robin boundary condition. If we take up the derivative, so du by dx is equals to 2x plus 2. So x is equals to 1, this value is equals to 4, or at x is equals to 1, this value is equals to u, which is equals to 4. So that's why you get the same analytical solution. This is just a coincidence. So here our pin solution exactly matches with the analytical solution. Now let's look at the periodic boundary conditions. So this periodic boundary condition is a little involved in understanding. So what we are exactly doing here is taking up this boundary. So this is our -1 boundary and this is our +1 boundary. So you are setting up a condition like u of -1 is exactly equals to u of 1. So what we are doing here is, so here u of -1 is equals to 0, and on the other end we are saying it like u of 1 is also equals to 0, but we are specifying it in another way like u of -1 is equals to u of 1. So this is called periodic boundary condition. Periodic boundary condition means at any two edges in the domain we set up the same boundary condition. So the boundary condition has to satisfy at two different edges. These periodic boundary conditions are useful for defining cyclic behaviors like wave propagation or any system where the start and the end points should match up closely. The idea is that the solution at one boundary, that is at A, is equals to the solution at the other boundary, that is at B. So we create a loop like this. So this is all about the periodic boundary condition, and in DeepXDE we set up the periodic boundary condition using these particular command periodic BC. This is a class in ICBC module of DeepXDE library. This function takes these many arguments. So the first one is the geometry. So this defines the geometry. So generally it can be a line or a rectangle or a polygon, that's up to you. And the second is component x. This is very important. This component x specifies the axis or spatial dimension along which the periodicity is enforced. It's not a specific coordinate, keep that in mind. So component x is equals to 0 indicates the first spatial dimension. Example, in 1D it is x, or in 2D problem, so we have x and y, right? But the first component is x. For example, in 2D geometry in a rectangle, x is equals to 0 represents we are enforcing the periodicity along x-axis. If the component x is equals to 1, we are setting up the periodicity along y-axis, meaning in 2D problem, so this defines your x-axis and this defines your y-axis. So this is component x is equals to 0 and this is component x is equals to 1. Okay, so that's how we define the periodicity. When we set up the periodicity x is equals to 0, we are setting up like the boundary condition across this edge and the boundary condition across this edge are same. So when we set up the component x is equals to 1, we are saying like the boundary condition across this edge and the boundary condition across this edge are same. So this is what the definition of this component x. And next is the unboundary. So unboundary is just like everything else, it is a function so that verifies whether the given point lies on the boundary itself or not. So this function takes two arguments, so that is x and unboundary variable. If the point in x lies on the boundary, then it returns true, else it returns false. And the next argument is the derivative order. So as I said, in DeepXDE you can set up the periodicity along the main variable or it's a derivative, the first derivative, that's it. So you cannot set up the periodicity across a second or third or higher order derivatives in periodic BC function. And the last is the component is equals to 0. This specifies the component of the solution. For example, in 1D problem all you have is u. For example, in 2D problem u is equals to u1 u2, whereas in 3D problem u is equals to u1 u2 u3. So you have to specify the component. This is the first component, this is the second component, this is the third component. Whereas in 1D problem all you have is u and that itself is the first component and the last component, no other components. Whereas in 2D you have this is the first component and this is the second component. That is what this component represents. So in our case, since it's a 1D problem and we are applying the periodicity along derivatives equals to 0, means 1Ds are defaults actually. So you don't need to specify the derivative order to 0 for 1D problem when you are applying the periodicity along its main variable, and you need to specify the component value. So after that, here we are defining the main periodic BC function. So as I said here, first I am sending the geometry and here I am setting the component x to 0, that is we are specifying the periodicity along x axis, and this is the boundary r. Boundary r, this tells whether the given point is there on the boundary or not. This boundary r is a function that takes two arguments only. One is the x, the coordinate list, and a special boolean value that is called on boundary. This checks whether the given value is on the boundary or not. So after we set up this periodic BC, and the next this data definition, neural network parameters, they are same as the previous Robin BC and the previous tutorial on Dirichlet and Neumann boundary conditions. So this is our loss pattern, and when we plot these values, so this is how we got the red one represents the pin solution and the blue dots represents the exact solution. So this is how we apply the periodic boundary condition. If you look at the periodic function definition in the DeepXDE documentation, so it also supplies two special functions called collocation points function and the error function. So what are these functions? This collocation point function returns the coordinates of the points on which the periodicity is applied. For example, after this plotting is done, I have created a special vector. So here I have used this geom function, and within the geom function I'm using this uniform points function. This geom and uniform point function are sub functions available in the DeepXDE library. You can extract some information that you want from this geometry object. So using the uniform points function from this geometry object, so I'm extracting 10 points within the boundary, so that is x, and from this x I'm using this BCR represents our periodic boundary condition. So here I am applying the collocation points to this x. So what it does is, so of these 10 points, it will gives you the coordinates on which the periodicity is applied. For example, these are all the 10 points that we have taken on which only on the boundaries 1 and -1 we applied the periodic boundary condition. And the second function is this error function. This takes these many arguments, so x, inputs, outputs, beginning, ending, and some variable. So this is not used in this function, so this is optional. And this function is called like this actually. So here first I am converting the periodic points to a tensor, that is a torch tensor, and the output that I am getting from model.predict. So the outputs are stored in this outputs tensor, and the beginning and ending are the, so if you given these points of boundaries, so of which what is the beginning location and what is the ending location, so those are the beginning and ending values, beg and end, and finally the residual value. So this residual value we are extracting from this error function of this periodic boundary condition. So I am sending the x represents the total values in the geometry, and inputs and outputs represents the periodic tensors, and beginning and ending are the row numbers here actually. When you send these things to the error function, you get this residual value, but in the training we do not exactly compare this residual value. We evaluate the mean squared error of this residual value, and we use it that for the training purpose to minimize the loss. So that's what we are evaluating here. So torch.mean residual square, so this gives us the MSC residual value, and this is the final value that we have got 2.427. If you look at here 2.427 e power minus 7, so in the end this is the loss value that we have seen in the training. 2.42 means 427 means 43 e power minus 7. So this is our the total training loss that we have got. And similarly this is our Dirichlet loss, and this is our residual, the main differential equation loss. So similarly, just like we extract the error from the periodic boundary condition, we can also extract the error from the Dirichlet boundary condition that we have applied at left boundary. So if you look at here x boundary, so at the left boundary we have only one point, that is -1. I'm just taking that in the x boundary, and inputs I just convert this one to a input tensor, and this one is the output tensor evaluated using this model dot predict, and I have got this beginning and ending function from this, and we have got this residual left from this BCL dot error function. So if you look at here, so if you go to Dirichlet BC, so this function now takes this error, not the one that is given in the periodic boundary. So this function takes this error function and evaluates the Dirichlet boundary condition loss. So when we evaluate the loss, so we have got the boundary residual as 3.05 e power minus 8. So if you look at the residual value, it is this 3.06 e power minus 8. So basically this is the explanation about the losses involved. Here we have only two boundary condition losses, right? So these are the two losses, and this is the main governing differential equation loss. And the same explanation applies here as well. This is the test loss of governing differential equation, and these two are the boundary condition losses. Okay. So here in this tutorial we have discussed about periodic boundary condition and Robin boundary conditions. So I have to demonstrate two important aspects here actually. The first one is, so if you look at here, this is our domain. We applied the boundary conditions on u of 1 and 1. For example, you take any middle value u of 0 maybe, and for example, or you take any other value u of 0.5 maybe, and this is u of 1. For example, if you want to apply a periodic boundary condition like this, one at the boundary and the other at the some intermediate point, or if you want to apply some boundary condition like this, what would you do? So this is on the boundary, but this is not on the boundary, this is some intermediate point. So what would you do in this such case? So the existing definition of a periodic boundary condition, the periodic BC, will not work in this case, because for the periodic BC function to work, the 2 points exactly on the two edges, two opposite edges. So that's it. So to overcome this complexity, or to implement this kind of some complex boundary condition, so we have to use a special boundary condition called operator boundary condition, this one. So this is the operator BC. So using this operator boundary condition, this kind of custom boundary condition implementation is possible. That is our first observation. And second thing is, if you look at this mean residual value from the Dirichlet boundary condition, so we have got the value as 3.05 e power minus 8. This is our Dirichlet loss value. Even though it is very small, but it's not exactly zero, because we want the boundary condition to be exactly zero, right? So that is not exactly satisfied, but it is in this problem, it is closely satisfied. For this problem, this is sufficient. but in some cases, in some complex cases like Burgos equation or the Navier-Stokes equation with some stricter boundary condition, so this kind of inappropriate losses is not sufficient. We have to exactly or accurately satisfy the boundary condition. This brings us to an important concept in boundary conditions called soft and hard boundary condition. Soft boundary condition allows some flexibility, which may result in some small errors like this at the boundaries. Though these errors are very small, insignificant, but in some problems these are very problematic. In hard boundary conditions, we strictly enforce these boundary conditions. So in our upcoming tutorials, we will look at this hard and soft boundary conditions and the way of applying custom boundary condition using this operator BC. So that's it for this tutorial. You have learned two important concepts, periodic boundary conditions and Robin boundary conditions in this tutorial, and you have also learned to apply them in DeepXDE. I hope this tutorial was helpful, and if you have any questions, feel free to drop your questions in the comment section. Thank you. Thank you for watching this tutorial. Happy learning.